Let us look at an interesting concept in Euclid's elements. We are given a straight line AB. What we have to do is find AC and BC two lengths such that the square on AB is greater than the square on AC by the square on BC, such that BC square is commensurable in length with AB square. Or we can say BC is commensurable with AB. So, how do we go about finding such lengths? Now, here, if you look at it, this can be rewritten as AB square is equal to AC square plus BC square. And that looks similar to the Pythagoras theorem, right? Which relates to a right angled triangle. So what we have to do is draw a right angled triangle. And since AB square is equal to AC square plus BC square, that means AB is going to be the hypotenuse. So that means we have to draw two straight lines such that the angle between them is 90 degrees, a right angle. And we know that that can be done if we have a semicircle. So AB will subtend a right angle on any point of this semicircle. Okay, so now we have this. Now let's proceed to the next step. What we do is we take two square numbers, 16 and 4. And these square numbers should be such that p square minus q square, 16 minus 4, should not be a square number. Now here, 16 minus 4 is 12, so it is not a square number. But suppose if we take this as 25 and this as 9, 25 and 9 both are square numbers. But when you subtract, what happens? You get 9. 25 minus, say, 9 gives you 16, which is a square number. Or 25 and 16, again you get 9, which is a square number. So those numbers we can't take. So p square minus q square should be such that it is not a square number. Another thing, p square should be greater than q square. Remember, we have this setup now, and we have these numbers set up. Now we use proportions to figure out one side of the right angle triangle. So p square is to p square minus q square, that is 16 is to 12, is equal to ab square is to ac square, the number that we have to figure out. Now we know how to arrive at AC. Product of extremes is equal to product of the means. So AC square is equal to, or if we take the square to the other side, it becomes square root of AB square times P square minus Q square by P square, which when we simplify becomes AB times square root of 1 minus Q square by P square. Here P square is greater than Q square, and let's say K is equal to Q by P. Then AC is equal to AB times square root of 1 minus K square. We have to figure out the other side. We have found AC. Now we have to find BC. For that, we straightforward use Pythagoras theorem. AB square is equal to AC square plus BC square. We know AB, we know AC. So BC square is equal to AB square minus AC square, or BC is equal to square root of AB square minus AC square, which is equal to square root of AB square minus, we substitute. So since we are talking of AC square, we get AB square times the square and the square root will cancel, and we are left with 1 minus Q square by P square. Now here AB square is common. So we take it out and we take it out of the square root itself so that it becomes AB times square root of, now here 1 is left out, minus again 1 plus q square by p square. So 1 minus 1 disappears. We are left with AB times square root of q square by p square. Again, these squares and the square root will disappear. So we are left with AB times K, where K is equal to Q by P. By the way, we found AC, we found BC. Now let's actually update this semicircle. Now we have to draw a line segment from A such that it is equal to AC. So how do we do that? We draw a circle with center at A and radius as AC. And we take the point of intersection between the circle and the semicircle. And we join A and C. So we have got AC. Now BC we can directly join. And we know that this is going to be a right angled triangle. So now AB square is equal to AC square plus BC square. And if we use values that we have arrived at, it comes to 6 square is equal to square root of 27 square plus square root of 9 square. Square root of 9 can be written as 3 also. So now we can say AB square is greater than AC square by BC square, where BC square is commensurable in length with AB square. BC square is square root of 9 square. AB square is 6 square. In length means you just ignore the squares. So square root of 9 is commensurable with 6. And square root of 9 is 3, is commensurable with 6. So we can use any two square numbers provided p square minus q square is not equal to a square to arrive at two magnitudes AC and BC such that AB square is greater than AC square by BC square, commensurable in length with AB square. Interesting, right? That's it for now.